in terms of new material. Conceptually, it's pretty straightforward. My preferred approach for applying the chain rule is to decompose the original function into separate functions, right? So, you know, composition of functions where you plug one function into another. Well, we want to do the opposite of that and then differentiate, right? There's other ways to do it. There's shortcuts. There's, hey, I guess you can call it mnemonic devices, you know, the rhymes and, you know, different strategies and stuff like that. But the one that kind of leads to the most amount of, I call it true understanding and learning is the decomposition technique, I believe. Because I mean, here's a shortcut rule for you. It's nice and enjoy it. But let me show you piece by piece what we're looking at here. Right. So the first example, we have y equals 2 plus the square root of u, where u is equal to x cubed plus 1. All right. So it's itemized here. It's saying find dy du, right, instead of dy dx. So I have a function y in terms of u that I can rewrite as y equals 2 plus u to the 1/2. This is just saying take the derivative of that. Just in your mind, say, okay, I'm working with a u instead of an x. And that's fine. dy du. 2 goes away. Derivative of 2 is equal to 0. U to the 1/2 would be 1/2 u to the negative 1/2. All right, so mission accomplished. Yay, we did it. All right, the second piece, we have u in terms of x. They're saying find du dx. So the derivative of the u equation in terms of x. All right, so du dx would be 3x squared. That's not bad. But then they say find dy dx. dy dx, we can get that, like I said, there's shortcuts, but we could get it from what we have written right here. Because if I take this expression, and I just mean the fraction itself, get rid of that, and multiply it by this expression, right? Because it's notation, but it's also a ratio. dy over du and du over dx, they're fractions, and fractions can be simplified, right? These two things multiplied would equal, you know, du's would cancel. It would be equal to dy dx. All right, so if I take this relationship, right, before that cancellation, all right, so I know it's going to be equal to dy dx, all right, this equal is going to bother me, like get rid of that. If I take that information and then make some substitutions, because I know that dy du is equal to this, and du dx is equal to this, multiplying them together would give me dy dx. However, I see this u staring at me here. When I see a dy dx, I tend to think, because it says, you know, when we read it, the derivative of y with respect to x, I tend to think that the expression that is the result should probably just be made up of x's, right? Sometimes we won't have control of that, as we'll see in the second unit. We'll just have to leave it in terms of multiple variables. And as you get further in your calculus careers, you'll see that. But since we do know what u is equivalent to, we can make that substitution. They told us right here that u is the same as x cubed plus 1. So I can now say that dy dx is equal to, instead of all this stuff here, pull out the u and replace it with what it really is. The x squared plus 1. cubed plus 1. And so it begs the question, okay, no, mission accomplished, we got that. What did we just figure out? All right. So we were originally given, all right, so we were given y equals 2 plus root u. We were also given u being equal to x cubed plus 1. What they gave us, or what, I'm sorry, that's what they gave us. What we just figured out, dy dx, is what the derivative would be if we replaced u in the original expression with what it truly was, because we could have done that. And then found the derivative of that. All right. So instead of making a composition early on and then differentiating it using a technique that would involve us decomposing the expression anyway, we took the derivative separately and put it all together so that we could determine what the derivative of this y equation right here would be. All right. And that ends up giving us ultimately what we were looking for. All right. Number 2 is very similar, except it's got trig functions in it, which is usually pretty scary for folks. But then you see number 3 looks completely different. It looks nothing like numbers 1 and 2, but that's what we're building towards. All right. So again, step 1, figure out what the derivative of y with respect to u is. 3 cosine u. All right. Cosine has a derivative of negative sine. Negative sine times 3 is negative 3 times sine. All right. Then also figure out du dx, which would be 4x. So we got these 2 pieces in the books. Dy dx is the product, right? Because dy dx is the same as saying dy du times du dx, right? If you were to cancel out the du's, you would get dy dx. That's how you know. So then multiply the corresponding expressions, because all I'm really doing is replacing. I'll actually write it underneath. It looks a little nicer that way. I'm replacing dy du with what I know it's equivalent to, negative 3 sine u. And I'm replacing du dx with what I know it's equivalent to, which is 4x. Right? And then the only thing that remains to do is swap out that u for what we know it's equivalent to. They told us that right in the open. They said u is equal to 2x squared. So my dy dx would be equal to negative 3 sine 2x squared times 4x. All right. And so again, what is that giving us? Well, originally they told us that y was equal to 3 cosine u. And they told us that u was equal to 2x squared. If we compose these 2 functions, put one function inside the other. Let me get light blue for those keeping score. If we put one function inside the other, we'd get y equals 3 cosine of 2x squared. The derivative of that is what we just figured out. All right. So what we want to be able to do is go straight from the function of y in terms of x to its derivative without having, well, essentially to break it all apart. But in order to do that, we want to learn how to break it apart first, find the derivative, and then we'll learn the shortcuts. but it's really the skill, the underlying theory that kind of drives everything towards true understanding. Right? I mean, I don't think I believed my teacher when they said that back in the day. I don't think I believe anybody I hear or see online when they say it now. I don't think I believe the textbooks when they say it, but it's true. You know, because the shortcuts, they'll get you an answer, but you won't know why you're doing what you're doing. Right? This gets you to the level of understanding. If you truly want to understand calculus to the point where you'll be proficient in it, not just this semester, but in future semesters, then this is something that you want to take seriously. Because I know some people have that mentality of like, oh, I'll worry about next semester. But the issue that you always find out is that it's not always the case that your teacher next semester cares about the previous semester, as in whether or not you learned the stuff the previous semester. Right? So, you know, take heed, as they say. Right? So in number 3, y equals the square root of 2x minus 1, what I'm going to do is I'm going to decompose this by creating a variable u, and that variable u will represent the more complicated part of the expression that I'm given. All right. So what we want to have is really only simple functions. All right. Not transformed functions, not ones that are shifted left, right, up, down, and all that stuff. We don't want what you see in the Desmos here, a times x minus h squared plus k. We just want like 2x squared at most. We want something that's nice and power rule-y. All right, nice and easy. All right. The basic rules of derivatives are the power rule, the constant multiple rule, and then throw in the basic trig rules. And those are the ones that we're really looking for. So if I let u be equal to 2x minus 1, and then write y so that it's equal to the square root of u, that'll get the job done. All right. Sometimes, you know, I'm not going to lie, sometimes you'll define your u thinking that you have it all figured out, and then you'll get down to business on it and you'll realize, you know, that's not quite what I was hoping for. Let me try something else. Right. But the benefit of writing it this way is if you have y equals u to the 1/2, that's power rule ready, as I like to say. Right. Where u is equal to 2x minus 1, we're ready to rock and roll. Because each equation, I should say, is differentiable, yes, but also easily differentiable. We could take the derivative in a very easy way. So dy du would be 1/2 u to the negative 1/2. Du dx would be equal to just a 2. If we're relying on this idea that dy dx is equal to the product of dy du and du dx, then it's just a matter of making a couple of quick substitutions. Replacing the u with what we know it is, 2x minus 1. By the way, the word of the day is tenet. T-E-N-E-T, tenet. 2x minus 1 to the negative 1/2 times 2. And so that would be my derivative. Okay, so that gets us from here all the way to here in one shot. Or if, you know, it doesn't really do that in one shot, but that's what it would be in terms of the actual derivative. You go back to what it is that you were trying to find the derivative of, it was this expression. The derivative of that expression is this expression. Now you could simplify further if you want, but again, think I've beaten this idea to death. We don't want to have to unless we're told to. All right. So the remaining problems here are all just practice. So I'll throw up an answer key, but what I wanted to do is shift gears and go through the practice test, because on the practice test, there is a nice chain rule problem. So I think we'll kind of get done what we need to get done by going through that. So I'm just going to pull those questions in to a notebook here so that I can mark it up and give you some good notes here. So let me stop this for